This lesson introduces a popular kind of static analysis called type systems. Type systems are often specified as part of the programming language and built into compilers or interpreters for the language. The main purpose of a type system is to reduce the possibility of software bugs by checking for logic errors. A common example of such an error is applying an operation to operands that does not make sense, such as adding an integer to a string in a Java program. A type system checks for such errors using a collection of rules which assign types to different parts of the program, such as variables, expressions, and functions. We will learn about the notation for type systems, various useful properties of type systems, and how type systems can even be used for describing other kinds of static analyses. Type systems are the most widely used form of static analysis. They are used in nearly all mainstream programming languages. One reason for this is that they are widely recognized as being important for maintaining the quality of programs. Let's look at an example of the kind of errors that a type system typically catches. Consider the following Java program, which defines a function f in class t in a file named t.java. When we compile this program using the Java compiler, it produces two type errors. The first error states that the if condition on line 4 expects its argument a to be of type Boolean, but it is instead of type float. The second error states that the return result c of the function f on line 7 is expected to be of type int, since the specified return type of function f is int, but it instead has type integer array. Java's type system prevents logic errors like these, which could cause the program to produce undesired results. Besides being a static analysis in their own right, type systems also provide notation, which is useful for describing a variety of static analyses, such as type checking, data flow analysis, symbolic execution, and more. To discuss type systems, we must first ask ourselves, what do we mean by a type? It is easy to label the number 2 an integer and the number 1.125 as a floating point number, but it isn't necessarily obvious how to define what a type is. To put it simply, a type is a set of values that constitute that type. For example, in Java, the type int is the set of all integers, at least those integers that can be represented in 32 bits of data. The double type is the set of real numbers that can be represented in a certain 64-bit IEEE standard. And the Boolean type is the set consisting of the values true and false. Moving away from primitive types in Java, we can come up with more complex examples. If we have a class named foo, then the foo type is the set of all objects of class foo. List of integer is the set of all list objects which contain integer objects. Note that list is a type constructor. It can be treated as a function which takes one type, in this case the integer type, and maps it to another type, in this case the type of lists of integers. We can also have function types. For example, int arrow int is the set of all functions that take an int as their argument and return an int as their result. Some examples of functions of this type would be the increment operation, a function that squares its input, and many others. Abstractions are an integral part of all forms of static analysis. Recall that in data flow analysis, we abstract the control flow of programs, and in pointer analysis, we additionally abstract the heap by lumping together objects allocated at the same allocation statement in the program. Why do we do this? The reason for abstracting program properties goes back to the undecidability of static analysis. We cannot reason directly about the infinite set of all possible concrete values. If we tried to, we have no guarantee that our analysis would terminate. Additionally, even for finite sets of concrete values, abstraction allows us to improve the performance of our analysis. The abstractions used in type systems are the types themselves. Each type represents a large, possibly infinite, set of concrete values. By abstracting away these large sets, we enable ourselves to reason about the values based on properties they have in common. A type is an example of what is known as an abstract value. in that it represents a set of concrete values. The Java type int represents all integers representable with 32 bits, and the list type represents the set of all list objects. In type systems, every concrete value must be an element of some abstract value. Therefore, every concrete value has a type. Let's introduce a simple typed language based on the lambda calculus. We will use this language to provide concrete examples for the abstract principles of type systems. Each expression E in this language evaluates to one of two kinds of values V. Integers, denoted here by I, but which may be any integer value, and functions, denoted as follows. Lambda x of type t yields E, where x of type t is represented by x followed by a colon followed by t, and yields is represented by an equal sign followed by a greater than sign. This notation means a function which takes an argument x of type t and returns the result of computing expression E. Both kinds of values, integers and functions, can be stored in variables denoted by x. Other identifiers may be used for variables as well. The plus operation requires that both E1 and E2 be integer valued expressions. Our type system will ensure that this requirement is indeed met in all executions of a program in this language. In other words, that E1 and E2 can never evaluate to a function value. Similarly, this operation denotes a call to a function E1 with argument E2, and there is a similar requirement on the kinds of values that E1 and E2 might evaluate to. A type system will also ensure this requirement. To meet these requirements, the system consists of two types corresponding to the two kinds of values in our language: an int type, which is the type of all integer values, and a function type denoted by t1 arrow t2, which is the type of functions. Note that the int type is a base type, whereas a function type is a compound type, as we will illustrate using an example program in this language. This example defines a function that takes an integer x as an argument and returns x plus 1. The type of this expression is int arrow int. This example defines a function which takes an integer x as an argument and returns x plus 1. The type of this expression is int arrow int. Then this function is applied to the integer 42, yielding the integer 43 as the value to which this program evaluates. To check your understanding of this language, let's do a quiz. Here we have listed 5 short programs. Lambda x of type int yielding x plus x, lambda x of type int yielding x plus x applied to 10, 42 applied to lambda x of type int yielding x plus 5, lambda x of type int yielding lambda y of type int, which in turn yields x plus y, lambda x of type int yielding x plus 10. Write the type of each program in the box beside it, or none if it is not typable. Note that in our type system, each typable program is guaranteed to have a unique type, so there will not be any ambiguity in the type of these expressions. Please use parentheses to disambiguate the type if needed. The first program is a function that takes an integer x and yields the expression x plus x. In other words, it is a function that doubles its input. The type of this expression is therefore int arrow int. The second program takes the function in the first program and applies it to the number 10. The result of this program is 20, which has the type int. The third program is not typable, as it violates a requirement of function calls, namely that the first expression in the pair must be a function, whereas here it is an integer 42. The next program is a bit trickier. It takes an integer x and returns a function that takes a number y and adds it to x. So, the type for the whole expression is the compound type int arrow int, where we put parentheses around the latter two ints in order to disambiguate the type. Note that putting parentheses around the first two ints would be the type of a function which takes a function from int to int and returns an int. The last program is not typable as it violates a requirement of the plus operation, namely that both its operands be integers, whereas here one of the operands is a function. Now that we have a better understanding of what types are, we will learn how to compute with them. That is, how to actually analyze programs using type systems. Type systems have a well-developed notation for expressing these sorts of analyses. In fact, a major part of defining a type system involves defining a set of rules showing how to check that a given program has a given type. In the next several slides, we will provide the notation for type systems, which consists of a set of rules that can be used to check that a given program has a given type. Later on in the lesson, we will discuss important properties of type systems, including how to infer the type automatically for a given program. Finally, we will see how to use the notation of types to describe other static analyses. If you have studied formal logic, you may be familiar with logical implications, or if-then statements. Inference rules in type systems are if-then statements, which are used to reason about the types of program fragments, such as variables, expressions, and functions. A rule of inference takes the form, if hypothesis is true, then conclusion is true, where the hypothesis and the conclusion are logical formulas. An example of an inference rule that might be used in a type system is, if E1 is an int and E2 is a double, then E1 times E2 is a double. Now let's start developing a standard notation for expressing inference rules. To build this notation, we will begin with a few small building blocks and then gradually add features as needed. The building blocks we will use are the inverted V symbol to represent the logical AND operation, also called the conjunction operator, the rightward pointing arrow to represent logical implication, that is, the if-then operation, and the expression x:(t) to represent the statement x has type t. When reading logical formulas aloud, the inverted V symbol can be read as the word AND, and the arrow symbol can be read as the word implies. Let's see how we can express the following English sentence in our notation for rules of inference. If E1 has type int and E2 has type int, then E1 plus E2 has type int. First, we can group the first two type declarations together with an inverted V to represent their conjunction by the logical AND. Then we can replace the if x then y construction with x arrow y, where x is the conjoined hypothesis and y is the conclusion E1 plus E2 has type int. Finally, we can replace the phrases x has type int with the notation x:(int, giving us the following inference rule. E1 has type int and E2 has type int implies E1 plus E2 has type int. Observe that in this formulation of the statement, we have two separate hypotheses which have been conjoined to form a compound hypothesis. Each separate hypothesis must be true in order to guarantee that the conclusion is true. In general, inference rules have the form hypothesis 1 and hypothesis 2 and so forth up to hypothesis n implies conclusion. An inference rule may have an arbitrary but finite number of hypotheses that must be fulfilled to guarantee the conclusion. Traditionally, inference rules are written in the following way. Each inference rule has one conclusion and 0, 1 or more hypotheses. The hypotheses are considered to be ANDed together. They must all be true in order to derive the conclusion. Inference rules without any hypotheses are called axioms. Their conclusions are statements we take to be fact without any preconditions. The hypotheses and conclusion all take the following form, where E is an expression and T is a type. This statement is called a type judgment. The pipe symbol followed by a hyphen is a symbol denoting the phrase, "It is provable that." Let's start building the type system for our example language by focusing on the rules for integers. The first rule we establish is that it is provable that I has type int for all literal integers I. For example, we could replace the letter I with 0, 1, 200, -3, etc. and the rule would still hold. Strictly speaking, we refer to such a template rule as a schema. And because there are no hypotheses in this rule, it is an axiom schema. We will name this schema int for future reference. The second rule we will establish is that if it is provable that E1 has type int and that E2 has type int, then it is provable that E1 plus E2 has type int. This is an inference rule schema as opposed to an axiom schema because there are more than 0 hypotheses. We will name this schema add. These rules thus serve as templates describing how to type integers and expressions containing the addition operator. By filling in or instantiating the templates, we can produce complete typings for expressions. Note that while hypotheses state facts about sub-expressions, conclusions state facts about the entire expression. Here is an example of a type derivation for typing the expression 1 plus 2. We first instantiate the axiom schema int, filling in the number 1 for I. To produce the axiom, it is provable that 1 has type int. Similarly, we instantiate the int axiom schema again. To produce the axiom, it is provable that 2 has type int. Then, we can take these two conclusions and plug them in as hypotheses for the inference rule schema add. Because it is provable that 1 has type int and 2 has type int, it is provable that 1 plus 2 has type int. This conclusion completes the derivation of the typing for the expression 1 plus 2. We have discussed typing for integer expressions, which in our simple language are restricted to sums. Using the rules we have established so far, we can derive a rule such as this one. If it is provable that E has type int, then it is provable that E plus E has type int. This schema carries the type information for E in its hypotheses. Now, we also want to apply typing rules for variables. However, if we try to axiomatically define X's type, we find that the axiom has no way of carrying the type information for X, and we don't want to impose a rule that all variables must be of a single type. Moreover, we can't provide type information via hypotheses because these hypotheses must eventually be derived from axiomatic statements. So we have run into a problem. How can we provide appropriate type information for a variable? The solution for our type system is to add more information to the rules. We can use an environment to give type information to free variables, such as X in the rule var. A variable is free in an expression if it is not defined within the expression itself. In contrast, a variable that is defined in an expression is called a bound variable. For instance, consider the expression lambda x is of type int yielding x plus y. Variable y is free in this expression, but variable x is bound. In a type system, an environment is a function which maps variables to types. For example, if we declare variable x to be an int in a Java program, the environment would map the variable x to the type int. The concept of an environment is general. In other kinds of static analyses, environments may map variables to other abstract values instead of types, as we will see later on in this lesson. Let's use the letter A to represent our environment, that is, our function from variables to types. We'll use the notation A pipe -e:\t to mean, under the assumption that variables have the types given by A, it is provable that the expression E has type T. Let's modify our previous rules, int and add, to include the type environment before the pipe hyphen symbol. And now we can write new rules, such as this axiom schema for typing variables, which we call schema var. Under environment A, it is provable that X has type A of X. A of X refers to the type assigned to X under the environment mapping A. Now we can make the last of the inference rule schemas for our language. We need to introduce rules for typing function definitions and function calls. For function definitions, we make the following rule, which we call def. Using our environment A, if it is provable that E is of type T prime, then it is provable that the function lambda x of type T yields E is a function of type T arrow T prime. Except we have a problem. In this expression E, x is a free variable and we need its type. We can fix this by explicitly requiring the environment to map x to type T. We do so by adding the notation x arrow T in square brackets beside the letter A in the hypothesis of this rule. Notice that this environment is the same as that in the conclusion of the rule, except that the environment in the conclusion of the rule does not give the type of x. This is correct since x is not a free variable in this expression. Rather, it is bound, that is, defined as the argument of this function. Finally, we define the inference rule schema call to give typing information for applications of functions to other expressions. If under the environment A, it is provable that E1 has type T1 arrow T2, and under the same environment A, it is provable that E2 has type T1, then it is provable that the result of calling E1 with argument E2 has the type T2. This concludes the set of schemas we need in order to completely type our example lambda calculus language. Notice that there is exactly one schema for each of the 5 syntactic expression forms in this language. Now let's look at how we would derive the typing for a non-trivial expression using these 5 schemas. Later, we will see how to algorithmically compute these derivations. But let's work through some by hand first to get a feel for them. A type derivation is a procedure which allows us to derive the type of a program if one exists. The goal of the derivation is to show that an expression has a given type derived ultimately from axiomatic statements. That is, there are no infinite or cyclic chains of hypotheses needing to show that some statement is true. In this slide, we will use our 5 schemas to derive the type of the program lambda x of type int yields x plus 1 applied to 42. See the instructor notes for a list of all the schemas for this language. We will work from the bottom up, checking to ensure that each single derivation fits the template for one of the rules we previously defined. The call rule schema requires that if applying expression E1 to expression E2 yields a type T2, then expression E2 must be of type T1 and expression E1 must be a function mapping T1 to T2. In this case, the lambda expression plays the role of expression E1, the number 42 plays the role of expression E2, and T1 and T2 are both the int type. The call rule schema is therefore satisfied. Notice that we maintain an empty environment for this template. There are no variables mapped to types. We use an empty array to represent this environment with no such mappings. Now let's derive the types of the hypotheses of the call rule. The int axiom schema allows us to assert that the literal 42 has type int without requiring any further hypotheses. If we look at the first hypothesis of the call rule, we see that we have a function definition. We therefore check to see that the def rule schema can be applied to this definition. This schema requires that if the conclusion is a function mapping a variable x of type T1 to an expression of type T2, then the hypothesis must be that it is provable that the output expression is of type T2 under the same environment with a single additional mapping of the variable x to the type T1. In this case, notice that the environment in the conclusion is empty and the environment in the hypothesis maps the variable x to the type int. Under this assumption, the hypothesis states that it is provable that x plus 1, which is the expression that the function outputs, is an int. Therefore, the def rule schema is correctly instantiated, and we now proceed to prove that x plus 1 has type int under the environment where x is mapped to type int. X plus 1 is an addition expression, so we now check that the add rule schema holds. Add requires that the hypothesis and the conclusion have the same environment, that the expression in the conclusion have type int, and that it be provable that the expressions in the hypotheses also have the type int. The schema has been correctly filled in, so now we must verify that each of the hypotheses are provable. Like before, we have the int axiom schema, under which the literal 1 is provable to be an int regardless of the environment. It is not a problem that x is in the environment but doesn't appear in the expression. We may still conclude that 1 is provably of type int. We therefore focus on the last unproven statement. It is provable that x is of type int under the environment where x is mapped to type int. This time we have a different axiom schema, var, under which we may prove that a variable has type t under the environment where the variable is mapped to type t. Because the var axiom schema may be instantiated by filling in t by the type int, the statement x has type int is provable. We are now done. All sub-expressions of the entire program have been shown to be provable from axioms, leaving no unproven hypotheses. Therefore, the derivation is complete, and we have proven that the full program has the type int. Now let's do a quiz to let you practice a type derivation on your own. Recall that in the previous quiz, you answered that the program lambda x of type int yields the function lambda y of type int yields x plus y has the type of a function mapping ints to functions from ints to ints. Let's suppose we wish to prove this type judgment under an empty environment. We take this to be the conclusion of a single derivation with the following hypothesis. Under the environment mapping x to type int, it is provable that the function lambda y of type int yields x plus y has type blank. This hypothesis itself is the conclusion of another derivation, whose hypothesis is under the environment mapping x to type int and y to type int, it is provable that blank has type blank. This type judgment is the conclusion of yet another derivation with two hypotheses. Under the environment mapping x to type int and y to type int, it is provable that blank is of type blank, and under the environment mapping x to type int and y to type int, it is provable that blank is of type blank. The two hypotheses in this topmost rule are derived from the applications of axioms, which are not shown for brevity. Complete the type derivation by filling in each of the 7 blanks with appropriate expressions and types. If you need them as a reference, the 5 typing schemas for this language are shown in the instructor notes. Let's again work from the bottom up. We need to apply the def inference rule schema to the last step in the derivation. This means we need the mapping x to int in the environment of the hypothesis, and we now need to prove that the type of the output expression is int arrow int. The expression lambda y of type int yields x plus y is now the conclusion of another derivation, which is another instance of the def inference rule schema. We add the mapping y to int to the environment in the hypothesis, and it is now required to prove that the expression x plus y has type int. Finally, to prove that x plus y has type int, we need to prove that under the environment x maps to int and y maps to int, x has type int and y has type int. This is an application of the add inference rule schema. This completes the exercise, but note that to complete this derivation, we would then need to use the var axiom schema twice, once to derive that x has type int and again to derive that y has type int. We are now done with the notation for type systems. Next, we will see some properties of type systems, such as, first, what guarantees do we have if a program type checks? That is, it is successfully typed according to the axiom and inference rule schemas, versus if the program does not type check. And second, algorithms to mechanically compute a type derivation if it exists. Let's return now to our Java example from the beginning of the lesson. In this case, the function f checks whether the variable a evaluates to true. If so, then it returns b, otherwise it returns c. Our lambda calculus language from earlier currently does not have the capacity to directly express this behavior. So let us extend the language to allow if-then-else statements. We'll need to add a new inference rule schema to check that if-then-else statements are correctly typed. The rule we'll add, which we'll call if-then-else, has 4 hypotheses. If under the environment A, it is provable that E0 has type bool, E1 has type T1, E2 has type T2, and T1 and T2 are equal, then it is provable that the expression if E0 then E1 else E2 has the type T1. Note that we are implicitly introducing a new type to our language, the bool type. We won't formally add all the required schemas to type Boolean expressions in our language, but you can try writing these rules yourself as an exercise. For the purpose of this lesson, we will assume Boolean expressions to be fully typed going forward. Also notice that we have a new form of hypothesis, T1 equals T2, which we do not preface with the is provable that notation. This expression is called a side condition. It is an additional constraint that must be satisfied in order for the inference rule schema to be instantiated. We'll use this rule several times throughout the remainder of the lesson to illustrate some key concepts. If we can successfully type the if-then-else statement, then the first hypothesis in the rule guarantees that E0 will be a Boolean, while the remaining hypotheses and the side condition guarantee that E1 and E2 will be of the same type. These sorts of guarantees are characteristic of sound type systems. Formally, we define a type system to be sound if and only if, whenever it is provable under an environment A that E has type T, and furthermore, whenever the environment A maps variable x to type T prime, then x indeed has a value v prime in that type T prime. Then E always evaluates to some value v in T. Sound analyses are extremely useful. If a program type checks according to a sound type system, then no errors of the kind checked by the type system can arise in any execution of the program. We say that a sound analysis verifies the absence of a class of errors. This is a very strong guarantee. The property verified holds in all executions of the program. This guarantee is encapsulated by Robin Milner's classic slogan, "Well-typed programs cannot go wrong." But soundness comes at a price. Because of the undecidability of static analysis, a sound analysis that always terminates must occasionally generate spurious errors or warnings, that is, false positives, due to the abstraction that the analysis makes. This means that the sound analysis is incomplete. An alternative approach is to use an unsound analysis, which allows us more control over the false positive rate. However, unsound analyses have the possibility of failing to detect errors, that is, producing false negatives. Type systems are sound analyses. While they may generate false positives on occasion, they will never produce a false negative. But most kinds of analyses for detecting bugs, so-called bug-finding analyses, are not sound. You can learn more about these kinds of analyses for Java and C by following the links in the instructor notes. Let's look some more at the notion of side conditions. These conditions occur in many type-based analyses. They are constraints that must be solved, that is, satisfied, in order to verify that the inference rule is properly applied. For example, consider the program, if a is greater than 1, then return lambda x colon int yields x, else return 10, in an environment where a has type int. The expression E1 in this program has the type int arrow int, while expression E2 has type int. Without the side condition, this program would be typed as a function mapping ints to ints. This would cause the type system to be unsound, as the program would not evaluate to the correct type if a were ever less than or equal to 1. Checking whether these side constraints can be solved is a separate algorithmic problem that we will cover in the lesson on constraint-based analysis. Another example of where side conditions occur are with recursive functions. functions which call themselves in their own definition. The constraint that must be satisfied is that if x is of type t1 and e is of type t2, then t2 equals t1. In fact, this is a bit too strict. It could be relaxed to requiring only that t2 is a subset of t1. Recursive functions yield constraints that are themselves recursive. The same holds for loops. We observed this phenomenon in the lesson on data flow analysis, wherein loops in programs necessitate multiple iterations of the chaotic iteration algorithm. That algorithm in reality is solving a system of recursive constraints, namely data flow constraints for computing the in-sets and out-sets of data flow facts at each program point. In general, the difficulty of solving constraints depends on the language of the constraints and the details of the application. We are now in a position to develop an algorithm to automatically type check programs. The basic algorithm is as follows. It starts by taking as input the entire expression to be checked and the environment in which it will be checked. It then determines which schema to use in attempting to type the expression. Typically, there is a unique schema for each kind of expression, which is the case for our simple language. In this case, the syntactic structure of the expression uniquely determines which schema to use. For languages where this is not the case, the algorithm tries to type the expression using each applicable schema and determines whether any schema succeeds. If the schema is an inference rule schema, then the algorithm recursively calls this procedure on each hypothesis of the schema. Then the algorithm attempts to solve any side constraints. Finally, assuming that all the hypotheses correctly type check and the side constraints are satisfied, the algorithm returns the appropriate type for the entire expression. In this instance of the algorithm, we show how an if-then-else expression would be analyzed. First, E0 would be checked to ensure that it is of type bool. Then, E1 and E2 would be analyzed to determine their types T1 and T2 respectively. Then the algorithm would attempt to satisfy the side constraint T1 equals T2. Assuming this constraint is satisfied, T1 would then be returned. Notice that step 1 requires the overall environment A, not just the particular expression being analyzed. Only then can we proceed to analyze the sub-expressions of the given expression. Intuitively, this environment A summarizes the result of the analysis of the remainder of the program in which this expression itself is a sub-expression. This particular style of analysis is called a global analysis or a whole program analysis, since it requires the entire program, or providing a model of the environment. It is also called top-down analysis, since it begins at top-level expressions and descends into sub-expressions. Let's look at an example of global analysis in action. Consider the following program, which consists of an if-then-else expression. We will show step by step how global analysis derives the following type judgment for typing this expression. We start out with the input as this entire expression and this environment A, which comes from the signature of function f. This environment summarizes the result of the analysis of the rest of the program in the following sense. Whenever f is called from the rest of the program, A can be assumed to be of type Boolean and B and C to be of type integer. In step 2, under this environment, we analyze E0, which in our example is the variable A, checking that it is of type Boolean. In step 3, under the same environment, we analyze E1 and E2, which in our example are variables B and C, giving types T1 and T2 as int and int respectively. In step 4, the analysis solves the side condition T1 equals T2, which indeed holds since it just inferred that both T1 and T2 are int. Finally, the analysis returns T1, which is int. In contrast to global analysis, there is local analysis, also called compositional analysis or bottom-up analysis. In this style of analysis, we first analyze sub-expressions, inferring the needed environments from the sub-expressions themselves. Since the separately computed environments might not agree, we constrain them to be equal. This allows us to generate a valid analysis for the entire expression. For example, in analyzing the if-then-else schema, we would not pass in an environment to the algorithm. Instead, the algorithm would analyze E0, inferring an environment A0 from this analysis, as well as checking that E0 has Boolean type. Then E1 and E2 would be analyzed, generating two more inferred environments A1 and A2 and obtaining types T1 and T2 for the expressions. Finally, the side conditions T1 equals T2 and A0 equals A1 equals A2 would need to be satisfied. If the algorithm is able to satisfy these constraints, then it returns the type T1 of the expression in the conclusion, as well as the environment A0 needed to prove that the expression is of type T1. Let's use the same example program to illustrate how local analysis operates. We have faded out the signature of the function f to emphasize the fact that local analysis does not require a model of the environment. We will show step by step how local analysis derives the following type judgment for typing this expression. In step 1, we analyze E0, which in our example program is the variable a. We infer this environment A0 necessary for checking that a is of type Boolean. In step 2, we analyze E1 and E2, which in our example are variables b and c, giving them types alpha and beta and environments A1 and A2 under which these variables have those corresponding types. Notice that unlike in global analysis, where both these types were inferred to be int, this time we have unconstrained type parameters alpha and beta. In step 3, the analysis solves side condition T1 equals T2, which constrains alpha and beta to be equal. The analysis also solves side condition A0 equals A1 equals A2, obtaining the following environment. Finally, the analysis returns T1, which is alpha, and A0, which is this inferred environment. Notice that the resulting typing is more flexible than what global analysis inferred. In particular, this expression has an unconstrained type alpha instead of int in the case of global analysis. Why do we have two kinds of type analyses? As usual, there are trade-offs between the two approaches that should be considered when deciding which one to apply. Global analysis is usually simpler than local analysis, as it assumes a model of the environment instead of inferring it itself. The drawback is that it may require a lot of extra engineering to construct models of the environment for partial programs. On the other hand, local analysis is more flexible. It can allow analysis of, for example, a library without a client. However, local analysis is harder to do in the following sense. It requires the algorithm to allow for unknown parameters in environments, which will be solved for later, such as alpha in the example we just saw, and more side conditions on such unknown parameters that greatly increase the complexity of the problem. We saw that type systems are sound in that well-typed programs do not go wrong in any execution. But type systems are incomplete. That is, untypable programs do not necessarily go wrong in some execution. Let's wrap up our discussion of the properties of type systems with a quiz that illustrates the incompleteness of the type system we designed for our simple language. Consider the following four programs. 42 applied to the function lambda x of type int yields x plus 5. The function lambda x of type int yields x plus 1. If true, then 1, else lambda x of type int yields x and the whole thing plus 1. And finally, if c not equal to 0, then lambda x of type int yields x, else lambda x of type int arrow int yields x applied to 1, and the whole thing applied to the expression if c not equal to 0, then 1, else lambda z of type int yields z. All of these programs are untypable according to the rules we have described in this lesson. However, not all of them correspond to programs that would exhibit an error on execution. Check the boxes corresponding to which of these programs can go wrong. That is, there is some execution on which an error would occur. Let's consider each program in turn. The first program is untypable because no rule allows for calling an integer like a function. Moreover, on every run of this program, this call to the integer would be encountered during execution, and it is undefined what should happen upon such a call. Therefore, this program goes wrong on all runs. The second program is untypable again because none of our schemas allows for the addition of a function to an integer, and on every run of the program, this ill-defined addition would be encountered. So this program is another that could, and indeed always would, go wrong. The third program is also untypable because the else clause contains a function added to an integer. However, notice that no execution of this program would ever encounter this ill-defined addition, since the Boolean expression always evaluates to true. This shows that our type system is incomplete. Even though this program would always evaluate to the integer value 1 and never encounter the bad code, we still reject it as ill-typed. The fourth program is untypable in our system because we require the then and else clauses of the same Boolean expression to evaluate to the same type. However, the functions output by the first Boolean expression have different domains, int arrow int and int arrow int arrow int. Similarly, the outputs of the second Boolean expression are int and int arrow int. Nevertheless, even though this program isn't typable, we can see that on every run of the program, no ill-defined behavior would be encountered. If C is non-zero, then the first Boolean expression would output a function mapping ints to ints, and the second Boolean expression would output 1, and we would then have the application of the function to 1. On the other hand, if C were to equal 0, then the first Boolean expression would output a function which takes a function mapping ints to ints and returns an int, while the second Boolean expression would output a function mapping ints to ints. And so the resulting function application would also be well defined. This gives us two examples, two false positives, where our type system is overly conservative about what it considers to be a valid program. While our type system can be proven to be sound, we will never be without these false positives, even if we try to introduce new rules allowing us to detect whether the then or else branches of Boolean expressions are followed. Earlier in this lesson, we promised that type notation would be useful in contexts aside from type systems. Indeed, they are useful for describing a wide range of static analyses. Instead of speaking in the language of types, we can interpret each part of a rule of inference in a different way. We will use E to represent the program or program fragment to be analyzed. T will represent an abstract value, which need not necessarily be a type that is computed for the program E. And instead of mapping variables to types, the environment A may now describe assumptions needed for aspects of E that are determined by the rest of the program. This will allow us to recursively analyze hypotheses of each inference rule, that is, the sub-expressions of the program, to prove that the program has some particular global property. What sort of properties can we reason about in this manner? As a starting example, let's use type notation to determine the sign of a numeric computation. For example, we would like to prove that the output of -3 times 4 is negative. Abstracting this particular computation, we can represent it as negative times positive equals negative. The abstract values that we will use in this analysis are plus, representing the set of all positive integers, 0, representing the set consisting of just the integer 0, and minus, representing the set of all negative integers. The environment in this system will be a mapping from variables to one of these three abstract values. Let's do a quiz on writing some example inference rules that we would want to add to our analysis. Under the environment A, if it is provable that E1 has value plus and E2 has value minus, then it is provable that E1 times E2 has value blank. Under the environment A, if it is provable that E1 has value plus and E2 has value plus, then it is provable that E1 times E2 has value blank. Under the environment A, if it is provable that E1 has value minus and E2 has value minus, then it is provable that E1 times E2 has value blank. And lastly, under the environment A, if it is provable that E1 has value 0 and E2 has value plus, then it is provable that E1 times E2 has value blank. As a quick check of your understanding, enter the appropriate abstract value for the conclusion of each of these 4 inference rules. Enter either the plus symbol, the minus symbol, or the number 0. Recall that a positive number times a negative number should be a negative number, and so we write down the abstract value of this expression as minus. Further, a positive number times a positive number should be positive, and so we write the abstract value of this expression as plus. Similarly, a negative times a negative is positive, and so we write the abstract value of this expression as plus. Finally, 0 times a positive number, or for that matter even a negative number, is 0, and so the abstract value of this expression is 0. Note that these don't constitute all the possible rules that we would want to add. We would need to add more to fully type all possible expressions. Not to mention that we would need to add axioms like int and var from a lambda calculus language. So far, we have described rules for deriving the sign of the product of two expressions. However, what if we want to describe the sign of the sum of two expressions? Let's add the following rule. Under environment A, if it is provable that E1 has value plus and E2 has value minus, then it is provable that E1 plus E2 has value what? We have a problem here. We don't have an abstract value that covers this case. How do we solve this problem? The solution is to add new abstract values to our system to make sure the system is closed under all operations. That is, there are no expressions with undefined abstract values. To our existing abstract values, we will add 2 additional abstract values. Top, which will represent the set of all integers, and bottom, which will represent the empty set. Notice that the abstract values no longer represent disjoint sets of concrete values. This is okay. This happens quite regularly in real-world programming. A subclass in an object-oriented language is an abstract value that represents a subset of concrete values represented by its superclass. Similarly, all of the abstract values in this example represent subsets of the abstract value top and supersets of the abstract value bottom. For this quiz, let's try to determine the appropriate abstract value for the conclusion in each of the following inference rules. Under the environment A, if it is provable that E1 has value plus and E2 has value minus, then it is provable that E1 plus E2 has value blank. Under the environment A, if it is provable that E1 has value plus and E2 has value plus, then it is provable that E1 plus E2 has value blank. Under the environment A, if it is provable that E1 has value 0 and E2 has value plus, then it is provable that E1 divided by E2 has value blank. And under the environment A, if it is provable that E1 has value top and E2 has value 0, then it is provable that E1 divided by E2 has value blank. Notice that we are also introducing inference rules about division now. Just use standard rules of arithmetic to determine your answers here. Fill in each of these boxes with a plus, minus, 0, the word top, or the word bot as appropriate. Let's start with the problematic example we considered earlier. If we add a positive number to a negative number, we could end up with a positive, negative, or 0 sum. Therefore, the abstract value of this expression is top. However, if we add 2 positive numbers, then the outcome will definitely be a positive number. Therefore, the abstract value of this expression is plus. Next, we consider the division of 0 by a positive number. This will definitely always output 0, and therefore the abstract value of this expression is 0. On the other hand, the division of any number by 0 is undefined, and so the abstract value of this expression is bottom. These rules would, of course, need to be augmented with several more to express the entire sign computation analysis. As an exercise, try to write down the rules to extend this system to the 4 basic arithmetic operations: addition, subtraction, multiplication, and division. You can even try to add the modulus operation if you like. Backtracking a bit, let's return to our analysis of the if-then-else expression from our lambda calculus language. It may seem like a digression from our current topic, but it will wrap back up nicely. Recall that in our algorithm's examination of the if-then-else expression, each of the sub-expressions were analyzed independently of one another. It didn't take into account the order in which the expressions were listed. It only checked that E0, E1, and E2 were of the appropriate types. We could have swapped E1 and E2 and the analysis would be unaffected. This is called flow-insensitive analysis, which you may recall from our study of pointer analysis. The analysis is independent of the order in which the statements appear in the program. In effect, it treats the program as a set of statements with little other structure imposed. In practice, you'll find that most type systems are flow insensitive. The reason for disregarding the control flow of the program is the usual reason for abstraction in static analysis. It simplifies the representation of the program state that our algorithm operates on. In particular, there is no need for modeling a separate state for each sub-expression. The resulting analyses are efficient and scalable, allowing them to be used liberally in many applications. The trade-off is loss of precision, which is the usual trade-off for speed in static analysis. To attain a faster, sound type system, we necessarily end up generating more false positives. Indeed, we have a constant time type checking algorithm that's perfectly sound. Just reject all programs. But of course, such a scheme, while fast and sound, is completely useless. If we are willing to sacrifice simplicity and efficiency in order to increase our precision, we can make our abstraction of the program state more realistic. One way to do so is to remain sensitive to control flow. In this case, each statement has an input environment and an output environment, and we order the analysis of sub-expressions by the environments that are produced. Therefore, the result of the analysis now depends on the order of the statements, allowing us to make a finer distinction between correctly typed and incorrectly typed statements. In the if-then-else schema example, we would start by proving that under environment A, E0 is a Boolean and then output a new environment A0. This environment then flows into the analysis of both the statement that E1 is of type T1 and that E2 is of type T2, each of which produce their own output environments A1 and A2. We would then need to solve the side condition that environments A1 and A2 are equal, in addition to the previous side condition that T1 equals T2. In order to prove that, under the environment A, the expression if E0 then E1 else E2 has the type T1 and the output environment A1. This kind of analysis is called flow-sensitive analysis. Now is where we start tying together our previous thread on different types of static analyses with this thread. The input and output environments in this kind of static analysis should remind you of something we saw earlier. In data flow analysis, we had in and out sets of program facts. These sets would play the part of the input and output environments. Therefore, data flow analysis, as we might expect from its name, is a flow-sensitive static analysis, which could be represented using type system-like notation. The environments shown previously in flow-sensitive analysis were fairly abstract. Let's look at a more concrete example by extending our rule of signs system with assignment statements. We add the following inference rule schema. Under environment A, if it is provable that E has value plus and results in environment A, then under environment A, it is provable that X assigned the expression E results in the environment A modified so that A maps X to the value plus. As we alluded to earlier, flow-sensitive analysis can be expensive. Our abstraction is more complex. Each statement has to maintain its own separate model of the program's state. Because we are keeping track of more information, we end up with a polynomial increase in cost over flow-insensitive analyses. We can further refine our model of the program state in order to improve the precision of our analysis. Recall that for the statement if E0 then E1 else E2, our analysis doesn't consider whether E0 is true or false. This leads to situations where dead code, that is, if E0 is always true or always false, can cause the program to fail to type check, or to a situation where the type system rejects a program that would have ill-defined behavior on a path that is logically impossible to take through the code. We saw both of these situations in a previous quiz. We call this sort of analysis path insensitive, as it does not consider whether certain paths through the code are impossible to take. It rejects a program that has a bad path, even if this path can never be taken, yielding false positives in the process. By making our analysis sensitive to program paths, we are able to eliminate this form of false positive at the cost of more complexity in our program abstraction. To do so, we augment our environment for each statement with a Boolean predicate P. If P is the predicate under which an if-then-else statement would be executed, then we add P to the input environment of the first hypothesis that E0 is a bool. For the second hypothesis that E1 has type P1, we add P conjoined with E0 to the input environment. And for the third hypothesis that E2 has type T2, we add P conjoined with not E0 to the input environment. Note that we are still retaining the distinction between the input and output environments for all the hypotheses. Additionally, we no longer solve the side constraint that the output environments A1 and A2 are equal. Instead, the conclusion allows for either of these to be its output environment based on the truth value of E0. Symbolic execution, which we will study later, is an example of a path-sensitive analysis. Note that path-sensitive analyses are also flow-sensitive, as we preserve the input-output environment ordering. As you might imagine, keeping track of these different execution paths can be quite expensive. In the general case, there can be an exponential number of paths to track compared to the number of statements in the program. But this complexity appears to be a necessary evil in many different applications. Path-sensitive analyses are often performed using backtracking instead of explicitly merging environments together. A single path is explored until termination, and then the analysis backtracks to a decision point before exploring another path. This allows clients to prioritize the exploration of paths that are potentially more interesting than others. For instance, in the case of a bug-finding tool, paths that are more likely to expose a bug. In this quiz, you will decide whether some sample programs can be proven to have certain properties by flow-insensitive, flow-sensitive, and path-sensitive analyses. For each of the following 5 programs, check the boxes corresponding to the kinds of analyses that can verify the specified property. The first program consists of 4 statements executed in the following order. X is assigned the string literal A, Y is assigned 5, Z is assigned the result of 3 plus Y, and W is assigned the result of X plus the string literal B. For this program, the property to verify is that there are no integer plus string errors. For this question, allow the analysis to assume that each variable is defined before being used, which is indeed the case for this program. For the second and third programs, the property to verify is that there are no divide by zero errors. The second program consists of 3 statements executed in the following order. X is assigned 5, Y is assigned 1 divided by X, and X is assigned 0. The third program consists of an if-then-else expression. If Y does not equal 0, then 1 is divided by Y, else Y. Note that the variable Y may have any integer value at the start of the program. For the next 2 programs, the property to verify is that locks are used correctly. That is, there is no attempt to acquire a lock on a resource already locked, and there is no attempt to release a lock on a resource that is unlocked. The fourth program consists of 2 statements executed in the following order: acquire lock R, release lock R. Allow the analysis to assume that R is not locked at the start of the program. Finally, the fifth program consists of two if-then statements executed in the following order. If z greater than 0, then acquire lock R, followed by if z greater than 0, then release lock R. Note that the second if-then statement is not nested within the first if-then statement. Also, note that variable z can have any integer value at the start of the program. Finally, as for the preceding program, allow the analysis to assume that R is not locked at the start of the program. The first program can be proven to be free of integer plus string errors using a flow-insensitive analysis, assuming that all variables are defined in the program before being used. Let's see why this is the case. A flow-insensitive analysis views this program as an unordered set of these four statements and effectively checks all possible orderings of these four statements for integer plus string errors. The analysis ignores orderings where a variable is used before being defined, since we allowed the analysis to make this assumption. Then, it is easy to see that on each remaining ordering, the analysis verifies that there is no integer plus string error. Since the original program represents one of these orderings, it follows that the flow-insensitive analysis has proven that it too is free of integer plus string errors. Since flow-sensitive and path-sensitive analyses are strictly more powerful than flow-insensitive analysis, it follows that they too can prove this program free of integer plus string errors. The second program cannot be proven by flow-insensitive analysis to be free of divide by zero errors. Because flow-insensitive analysis considers the statements as an unordered set, it does not know that the assignment of 0 to x comes before the assignment of 1 by x to y. However, flow-sensitive analysis does consider statement order, so it will know that x will not be 0 at the execution of the division operation. Because path-sensitive analysis is strictly more powerful than flow-sensitive analysis, it will also be able to verify that the program will not throw a division by zero error. The third program cannot be proven even by flow-sensitive analysis to be free of divide by zero errors. Flow-sensitive analysis, while it does keep track of the order of statement execution, it does not keep track of which branches are taken at any given decision point for the program. For example, if 1 by y and y had been switched so that the program read, if y does not equal 0, then y, else 1 divided by y, a path-insensitive analysis could not tell the difference. All it would know is that either y or 1 divided by y could appear after the check that y does not equal 0. Therefore, it could not prove that the division by y won't throw an error. However, a path-sensitive analysis would be able to tell the difference if we were to swap the positions of 1 divided by y and y in the if-then-else expression. In particular, it could prove that if 1 divided by y is in the y not equal to 0 branch, then an error would not occur. Now, for the fourth and fifth programs, the analysis must prove that the program does not acquire any locked resources or release any unlocked resources. The fourth program relies on the particular statement execution order in order to ensure that the lock on R is not released while R is unlocked. Therefore, a flow-insensitive analysis could not prove that R is not improperly unlocked, whereas a flow-sensitive analysis, and therefore a path-sensitive analysis, could. To verify that the fifth program does not have any locking errors, certainly requires at least flow sensitivity to detect that any lock acquisition comes before lock release. However, just flow sensitivity is not sufficient in this case, as it is too weak to recognize that if z is greater than 0, then the then portion of both branch points must be taken. Path-sensitive analysis would be able to recognize this fact, and so path-sensitive analysis is able to prove that the program does not have any locking errors. We have discussed different kinds of analyses and their abilities to detect errors in programs with different structures. While we have used the notation and terminology of type systems in this discussion, The typical applications of these analyses often have different names and purposes in practical applications. While it is certainly possible to create a type system that is flow sensitive or even path sensitive, we normally think of type systems as flow insensitive analyses. Flow sensitive analyses are usually associated with data flow analyses, and symbolic execution is a prototypical path sensitive analysis. However, these lines have become more blurred lately. For example, in the research literature, it is not uncommon to come across flow-sensitive type systems and path-sensitive data flow analyses. This concludes our introduction to type systems and their usefulness to static program analysis in general. In this lesson, we have learned what a type is, an abstract value consisting of a set of concrete values having that type, how to compute the types of programs using derivations from type rules, the properties of type systems: soundness, that is, guaranteeing no false negatives; incompleteness, that is, the occurrence of false positives; and global versus local type checking. How to describe other kinds of static analyses using the notation of type systems, and the strengths and costs of flow insensitive, flow sensitive, and path sensitive analyses. We have only scratched the surface of the literature on type systems in this lesson. The study of type systems is an active area of research with many fruitful results. If this lesson has piqued your interest, we have included a list of resources in the instructor notes for further reading on topics in type systems.